Two giants, one rivalry. We're talking about the Airbus A380 and the Boeing 747. Both have changed the course of aviation forever and stand as legends today. But the real story isn't in their size or fame, it's their wings. Vast structures that do more than keep the aircraft flying. They explain why one of these aircraft survived and the other vanished too soon. The Boeing 747 first flew in 1969. At the time, jet travel was booming and airports were crowded. Airlines knew they wanted something revolutionary. Boeing gave them a wide body with wings spanning 195 feet that was capable of flying over 5,000 miles nonstop. For its era, the 747's wing was an engineering marvel, designed almost entirely with wind tunnels and hand-drawn calculations. Fast forward to 2005, Airbus unveiled the A380 with wings stretching nearly 262 feet across. Unlike the 747, these wings were built in the computer age using advanced simulations and composites. They weren't just for the present. Airbus deliberately designed them to support a future stretch version, the never-built A380-900, which could have carried over 900 passengers. That ambition shaped everything about their size and strength. On paper, the A380 dominates. Its wing area is over 9,100 square feet compared to the 747-400's 5,500 square feet. Each wingtip of the A380 towers higher than a three-story building when parked. With this sheer scale, the A380 can generate enough lift to carry more than 1.2 million pounds into the air. The 747's wings, though smaller, were designed with stricter limits. Boeing engineers had to keep the span below 200 feet so it could fit into existing hangars and taxiways. That restriction forced them to prioritize efficiency. This created a wing that balanced range and capacity. Bigger wings can mean more lift, but they also bring problems like more drag, weight, and eventually cost. Airbus went big because it believed hub-to-hub super jumbo travel was the future. Boeing kept things moderate, betting airlines wanted flexibility. The difference in wing size reflects the very strategies that shaped their destinies. Quick question before we move on. Which giant do you think had the better start, Boeing's 747 or the A380? Let us know in the comments. And if you like this video so far, don't forget to subscribe to the channel. The 747's wings were largely aluminum alloy, built with 1960s technology. Later updates added composites and secondary structures, but the core remained traditional metal. The A380's wings, built in Broughton, UK, are a mix of aluminum and advanced carbon fiber composites. Entire trailing edges are carbon reinforced. Each wing weighs around 40 tons empty and was so large it had to be shipped by barge and special transport convoys across Europe before final assembly in Toulouse. If you have ever seen a 747 liftoff, you'll have noticed that its wings arch upwards several meters. That flex isn't a weakness, it's strength. It's how aluminum absorbs turbulence and redistributes stress. Pilots often describe the 747's wing flex as alive, a graceful movement that reassured them the aircraft was working with the air, not against it. The A380 takes this even further. During heavy loads, its wings can flex upwards by nearly 7 meters at the tips. Airbus achieved this by blending metal with carbon fiber composites, which made the wings lighter but also incredibly flexible. This flex smoothed turbulence so effectively that passengers often describe the A380's ride feeling like gliding on rails. Flexibility is why these wings last for decades and can endure takeoffs, landings, and the stress of unpredictable weather storms without cracking under strain. The 747's wing sweep is about 37.5 degrees, ideal for cruising near Mach 0.85. Early versions had no winglets, but in the 1980s, Boeing added them to the 747-400, cutting down drag from wingtip vortices. The later 747-8 went even further by replacing winglets with elegant raked tips and a recontoured airfoil. This gave it a lift-to-drag ratio comparable to modern twin jets. The A380's wings are less swept, around 33.5 degrees, and also much broader. Instead of winglets, Airbus used upward curved wing fences. Engineers debated using raked tips like Boeing's, but the sheer span of the A380 made fences more practical for controlling turbulence. Despite their different solutions, both designs achieved efficient long-haul cruise. The A380, despite being heavier and larger, manages fuel burn per passenger close to the 747-8. The 747 relies on a remarkably complex high-lift system for its time. Along the leading edge are 14 Kruger flaps and triple-slotted flaps on the trailing edge. In full landing configuration, the 747's wingspan visually grows and increases both surface area and curvature. Pilots have described the drag from these flaps as so immense that it feels like throwing an anchor out of the cockpit. But this mechanism allowed a 400-ton aircraft designed in the 1960s to land at speeds manageable for major airports. The A380's system takes that complexity to a higher level. Its leading edges use full-span slats which extend smoothly to reshape airflow. On the trailing edge, Airbus added huge flaps working alongside drooped ailerons, so even the roll control surfaces assist in generating lift during takeoff and landing. The flaperons are hybrid surfaces almost the size of a regional jet's wing that blend the function of both flaps and ailerons. At full extension, the A380's wing area increases by nearly 40%. Few passengers notice, but these hidden transformations are the reason these giants can rise gracefully from runways rather than needing impossibly long airstrips. The A380 also features one of the most advanced fuel management systems ever installed on a passenger aircraft. Its wings contain multiple tanks and fuel is actively moved around mid-flight to adjust the aircraft's center of gravity and relieve bending stresses. This wing bending relief system means less fatigue and lower maintenance over the years. Each A380 wing can carry over 250,000 liters of fuel. Airbus engineers joke that the A380's wings fly with fuel twice, because once to power the engines and then once to balance the structure. The 747 also uses wing tanks, but its system is simpler. Fuel distribution there is primarily for balance and trimming the aircraft's nose attitude and not for reducing wing stress. For its time, it was advanced, but the A380 turned fuel into an active tool of structural management. It's one of those invisible differences that most passengers will never know, but one that highlights just how much wing design evolved over 40 years. Passengers often describe the A380 as the smoothest ride they've ever felt. Its massive wings lower wing loading, meaning each square meter of surface carries less weight. Combined with flex and active gust load alleviation from fly-by-wire controls, the turbulence feels muted. The 747, with its higher wing loading, reacts more sharply. For some, this makes it feel more real, like a machine responding dynamically to the air. For others, it means bumpier rides. The difference comes directly from the wings. One is calm and ship-like, the other lively and bird-like. Both unforgettable in their own way. Boeing deliberately capped the 747's wingspan under 200 feet because of infrastructure to ensure it could fit into existing hangars and gates. Otherwise, airports would have had to spend millions in upgrades. That decision alone gave the 747 a huge commercial advantage. Airlines didn't just buy a plane, they bought global access. The A380 broke that convention with a wingspan of 262 feet. Suddenly, regulators had to create a whole new category, Code F, for super-wide aircraft. Airports that wanted the A380 had to widen taxiways and reinforce runways. Singapore Changi, Dubai, and London Heathrow spent heavily to welcome the jet, but many airports didn't. In the United States, only a handful of airports like Miami, JFK, and LAX upgraded to handle it. Others simply couldn't justify the cost for one aircraft type. This meant that, ironically, the very size that made the A380's wings engineering masterpieces also limited the jet's reach. The 747's wings helped it conquer the world, but the A380's wings became part of its struggle. The 747's wings symbolize balance. Big enough to revolutionize travel, but modest enough to fit the world's infrastructure. They carried astronauts, presidents, and millions of everyday travelers. Eventually, their design went on to inspire countless later jets like the Boeing 777 and even the 787 Dreamliner, which borrowed lessons in efficiency and wing flexibility. The A380's wings symbolize ambition. They were designed not just for today, but for a tomorrow. Airbus was certain would arrive, where airports funneled hundreds more passengers onto each flight, and where bigger always meant better. These wings were sized for the A380-900 that was never built. It was a stretch version that would have carried over 900 travelers across continents. In reality, that demand never materialized. The aviation market shifted, and airlines preferred more fuel-efficient twins like the 787 and A350 that could fly directly between secondary cities. Two sets of wings, one pragmatic, one visionary. One carried the Queen of the Skies for 50 years. The other gave us the largest passenger plane ever built, but one whose time ended too soon. The wings of the A380 and 747 are proof of engineering that's turned into legend. One proved that practical design can endure for generations. Tell us in the comments, which wings impress you more, the timeless 747s or the powerful A380s? Stealth, precision, power. 3 words, and behind them, an aircraft unlike anything the world has seen before. This is the B21 Raider, built over 3 decades and designed to carry nuclear and conventional weapons both. Its alien-like flying wings sit at the heart of its mystery. By the end of this video, you'll understand why the B21 uses a flying wing design, how its wings balance lift with near invisibility, and why this shape could redefine the future of aviation. The B-21 wasn't created to haul passengers or freight. It was designed to penetrate the toughest air defenses on Earth. To do that, Northrop Grumman returned to the design philosophy of the flying wing. Unlike conventional aircraft where wings attach to a fuselage, the B-21's body and wings flow as one continuous shape. This reduces drag and eliminates the radar reflective corners that traditional aircraft can't avoid. The result is a jet that doesn't fly, it disappears. The Raider's wingspan is about 170 feet, and it is optimized for stealth and efficiency. Every curve and angle was shaped to balance lift and invisibility. What many don't realize is that this philosophy dates back to the Northrop YB-49, a flying wing from the 1940s that failed because it was too unstable without modern flight computers. The B-21 is the realization of a concept 80 years in the making. Its wings were not too large to limit base options, but also wide enough to ensure long range. In other words, the wings were built for the sky as well as global deployment. At the heart of the Raider's design is its blended wing body. The wing doesn't stop where the fuselage begins. Instead, they merge. This seamless curve gives the B-21 exceptional lift-to-drag performance and enables intercontinental range without refueling. The wing's airfoil is carefully sculpted to remain efficient at high subsonic speeds. Unlike fighters designed for supersonic bursts, the B-21 prioritizes long endurance. Its broad, flat wings generate steady lift while minimizing drag across thousands of miles. The smooth edges, lack of vertical tails, and precisely curved leading edges all scatter radar waves instead of reflecting them back. The B-21's wings are stealth weapons in their own right. Why subsonic? Because stealth and supersonic rarely mix. Shock waves at supersonic speed create heating and turbulence that betray stealth aircraft. By staying subsonic, the B-21's wings maximize both endurance and invisibility. Analysts even suggest its wing body blend may give it the highest aerodynamic efficiency of any bomber ever built. To achieve this, Northrop Grumman relied heavily on composites. Carbon fiber reinforced structures form much of the wing, making it lighter yet stronger than metal. Advanced radar-absorbent materials are layered into the skin, turning the wing itself into part of the aircraft's stealth shield. Internally, spars and ribs are arranged to maximize strength without adding weight. Flexibility is built in the wings and they can absorb turbulence rather than transmit it to the airframe. The Raider's wings need to endure the forces of flight and also decades of missions across varied climates, like icy high-altitude patrols and hot desert takeoffs. Unlike its predecessor, the B-2, the Raider's wing coatings aren't simply painted on. They're believed to be integrated into the composite layers themselves, reducing the need for constant touch-ups. This means the B-21's wings are stronger and stealthier. One of the most remarkable aspects of the B-21's wing is how it helps the bomber cover such immense distances. The broad span increases aspect ratio, reducing induced drag and improving lift efficiency. Inside, the wings double as fuel tanks, holding the reserves necessary for global strike missions. The efficiency of the airfoil allows the B-21 to fly farther on less fuel than comparable bombers. Reports suggest its range may exceed 6,000 miles without refueling, and with aerial tankers, it's effectively unlimited. For a stealth bomber, that range is essential. It allows the Raider to approach from unexpected directions, exploiting its wings not only for lift, but for strategy. While Northrop Grumman has kept most structural tests classified, engineers have confirmed that the B-21's wings are built for extreme endurance. The Raider's wings flex naturally in turbulence. This isn't visible from a passenger cabin because there isn't one, but it is a vital part of the bomber's durability. Flex helps distribute loads, reducing stress on critical joints. It also improves stealth. By smoothing out flight motions, the Raider presents a more stable radar profile. Few images exist of the B-21 in flight, but the promise is clear. The wings were designed not only to carry weight, but to carry a nation's nuclear and conventional deterrent on missions that may last for entire days. Do you think future passenger planes will use a flying wing design like the B-21? Tell us in the comments below. And if you like this video, don't forget to subscribe to the channel. It helps us make more videos just like this one. The B-21's wings are full of hidden systems. Embedded within are advanced fuel plumbing, environmental systems, and electronic warfare equipment. One of the most closely guarded secrets is how the Raider integrates its weapons bays with the wing body structure. The edges must remain smooth to preserve stealth, yet the aircraft can still open massive internal bays to release precision-guided weapons. Engine inlets are also buried in the wing body blend. By channeling air smoothly into the engines while hiding the fan blades from radar, the Raider's wings double as stealth covers. What looks like a clean curve hides a labyrinth of systems that let the aircraft stay invisible while fully operational. Some analysts believe the wing edges also hide embedded antennas and sensors, making the wings part of the Raider's intelligence network. Others speculate the space within could one day host directed energy weapons. What's hidden in the wings may be as revolutionary as the wings themselves. Stealth is about how wings manage energy. The Raider's wing edges are carefully aligned with its planform, so radar energy reflects away rather than back. The lack of vertical stabilizers means no radar hotspots. Even infrared is managed. The wing's surface materials help dissipate heat and prevent sensors from spotting hotspots across the span. By combining aerodynamics and materials, the B-21's wings give it a cloak of invisibility across multiple spectrums. The Raider's wings are evolutionary. They're smaller, cheaper, and easier to maintain, but just as effective. The Raider proves stealth can advance without growing in size. Building the Raider's wings required digital design from the ground up. Unlike older programs where prototypes were hand-built, the B-21 was designed entirely in 3D modeling environments, with every rib, spar, and panel mapped digitally. Sections of the wing are fabricated using automated composite layup machines, cured in massive autoclaves, and assembled in climate-controlled facilities. Robotics reduces human error, ensuring stealth-critical tolerances are met down to millimeters. The B-21's wings represent 21st-century digital manufacturing because they are faster, more precise, and more cost-efficient. Stealth aircraft are notorious for being difficult to maintain, but the Raider's wings were designed to change that. The B-21 uses modular materials that are easier to replace. Inspection ports and digital diagnostic systems are built into the wings and allow crews to detect structural stress or stealth coating wear without stripping the entire aircraft. This means the B-21 can spend more time flying and less time grounded. Perhaps most important are the wings that are built with open architecture in mind. As technology advances, sensors or electronic warfare systems embedded in the wings can be upgraded without redesigning the entire structure. The B-21's wings cut down on maintenance hours drastically. Think of it as stealth wings built not only to fight wars but to survive the grind of decades of service. The B-21 Raider's wings symbolize the shift from brute force bombing to subtle surgical capability. They prove that wings can be more than aerodynamic tools, and they can be platforms for stealth, sensors, as well as survivability. They also hint at where aviation is headed. The same principles guiding the B-21, like its blended wing body, composite structures, and stealth shaping, are being studied for future commercial and military aircraft. NASA has already flown experimental blended wing body aircraft, like the X-48, which demonstrated fuel savings of up to 30% compared to conventional designs. Airbus too revealed the Maverick concept, a small demonstrator that looks more like the B-21 than a traditional airliner. What began as a secret bomber project may ripple into civil aviation in ways we can't yet imagine. One day, boarding a passenger jet might feel less like stepping into a tube with wings and more like stepping into the future of the B-21 itself. The wings of the B-21 Raider are symbols of a new era. They lift an aircraft as well as a strategy built on invisibility, range, and endurance. If you enjoyed this breakdown, give it a like, subscribe, and tell us in the comments which part of the Raider's wings amazed you the most. We'll be back next time with another deep dive just like this.